Bismillahirrahmanirrahim. This video is about separately excited DC generator, and this I have taken from the lecture notes of Dr. Sitar S. Kareem in Electrical Engineering Department, University of Anwar. And here I'll be trying to explain the solved example, exercise 8.17. And for this, I have been requested by a student. So let's see. First of all, there are some characteristics. One is the called open circuit characteristic. That means when there is no load connected, what is the characteristics of the generator? And it is basically plotted between the IF, that is the field current, and the E, or the generated voltage. And these are some of the values. Now this is in tabular form, and the doctor has used this as the OCC, but normally in most of the books it is given in the shape of a graph. What I have done is I have taken these data, and through the help of the MATLAB I have just plotted it, so I feel more comfortable with the graph. But anyway, both will work, and this graph is for 850 RPM. There is another type of a characteristic that we'll be talking about, that is called the terminal characteristics or external characteristics. So it is the plot between the terminal voltage Vt and the load current. And so you can see this is the ideal scenario, but there will be some drop because of IA-RA drop. And this diagram is when there is a compensating winding. And when there is no compensating winding, then this will drop further and it will become like a curvature slightly curved. So these two graphs we have to keep in mind. And now coming on to the question. Now there are 5 parts of the question. The table represents the open circuit characteristics of a DC machine at 850 RPM. So this is the table. The machine has a shunt field winding of 600 turns and a resistance of 20 ohm. The armature circuit resistance is 0.025 ohm. Neglect the demagnetizing effect of the armature reaction and the brush constant drop. Okay, now this is the question, and this is the first part of the question. But let me first have the machine diagram. So it will be something like this. This is the separately excited field, and this is the armature circuit. And I have now plugged in some of the values that are given. Like the field winding is connected in series with a variable resistor and is supplied by a 330 volt separate source. So this is the field winding. There is a fixed resistor and there is a variable resistor. Now this variable resistor is called field control resistor, or simply FCR. And in this case, the input voltage is 330 volt. Now the question number 1.1 says that the field control resistor is set to 10 ohm. So this is 10 ohm full. Plot the external characteristics up to a load current of 300 ampere. So external characteristics, is between V and Vt and I load. And the next part is find the load current and voltage regulation when the terminal voltage is 220 volt. So we'll tackle them each. The first one is to plot, and these are the values that are given. FCR is 10. The current will be varied, or the data that this plot will obtain for the current from 0 to 300 ampere, because that's the maximum current. We have to calculate the voltage regulation VR also, and the terminal voltage is given 220 volt. We need to find the terminal voltage Vt and the load current IL for this external characteristics plot. This formula, I hope you recall, this is for the generator. The generator EA is greater than the terminal voltage. So EA minus the armature drops will give us the terminal voltage. Now we can find EA from the OCC table. So the table that we discussed, from there we can find EA. And but this we have learned that the OCC table is between IF and EA. So we have to know IF first of all to find EA. And to find IF, now this is the IF. We have the voltage, so we need to find this whole resistance. And in this case, the total resistance we are calling RF, which consists of FCR plus RF dash. So FCR is set to 10, RF dash is given in the circuit 20, so RF is 30. Now IF is voltage divided by resistance. So IF is V shunt or V field divided by RF. V field is 330. RF from here is 30. So IF is 11 ampere. And now if we look at the table for IF of 11 ampere, the EA is 248 volts. So we'll use this. The EA is 248 volts from the open circuit characteristic table. And now we put the value of EA in this table, 248. IA we have to assume from 0 to 300, and RA is also given in the book, which is 0.25. We'll use this equation to find values of VT for different values of IA. Okay, so this is the equation. Let's put IA is equal to 0, then we get a value of VT, then I is 30, we get a value of VT, and so keep putting in the values, and finally for 300 ampere, the 173. So the graph will now look like this. This is the table of the output characteristics. We are putting these values that we have assumed, 0 and 30, then 60, 90, 120 up to 300. And here we are writing the voltages calculated. So 248 in the second case, 240.5, and the last case 173. So I hope you can calculate all these to form this table. And we can plot this again. If you know MATLAB, very simply you can just put in these two parameters and you can plot this graph. So this is the external characteristics graph, and it is something similar to what we had seen in the first slide. This is the characteristics graph actually given in the books. Ours is quite similar. Part B, we have to find the load current. Now this is the armature portion of the circuit, the load current, which is same as armature current. Find the load current and the voltage regulation when the terminal voltage is 220 volt. Again, we'll use the equation that we know. From here, IA will be EA minus VT over RA. So we know all the values. EA we had got from table 248, VT is 20, and RA you can see from here it is 0.5. So IL will be 112. This is the load current. And now the voltage regulation is, the formula is V no load minus V full load divided by V full load. Now V no load is the EA that we got, that is at no load, and 220 is at full load. So we'll plug in the value. So 248 minus 220 divided by 220. So the regulation is 12.73%. So that means at load the output voltage drops. by 12.73%. This is not a very good arrangement. Okay. Now, question number 1.2, repeat question number 1.1 for FCR 20. Earlier we had taken FCR as 10. Now he's saying that if we increase the control resistor to 20, what will be the effect? Same thing, we have to plot and we have to find the load current and voltage regulation. We exactly follow the same technique. RF total with FCR 20 is now 40. IF putting in the formula is now 8.25. And from the table now we have to find the EA. This is the table. So 8.25 will be something between these two, 8 and 9. And the difference here you can see is of 11. So roughly about 3 we add with this, 2 to 5 maybe. Okay, so from the table of the graph, EAA is 2 to 5 as against 248. Now in the previous question, when this was 10, then we had EA 248, but now EA has dropped to 225. And current again, the same formulas. Now here we are using new value 225, so the load current is 20 ampere. I'm just comparing everything that the earlier with the 10 ohm FCR, the load current was 112 ampere, and now the load current has reduced by about 5-6 times, so it's 20 ampere. So one thing you can see that you can easily control the load current by varying this FCR resistor or field control resistor. And what will happen to the regulation? Again, we are putting the values 225 minus 220 divided by 220. So the regulation is now 2.3% as against 12.73%. So when the current is low, obviously the terminal voltage drop will be less. And this is 2.3% drop, or the regulation is 2.3%. Okay, now the next part is the plot. So here we are just changing the value of the new EA 225 and selecting all the values of A as we did in the previous case. We can find the VT, and I hope you can do start from 0, then IA 30, then 690, etc. And you can get a plot of VT over IA. So I'll skip that part. The third part of the question, which is 1.3, find FCR to make the terminal voltage 220 volt at a load current of 180. So both things are fixed. Output voltage is fixed and the load current is fixed. Now we have to find the value of this resistor FCR. And this is the table that we are going to use, the OCC table. So here also now the FCR we have to find. And this formula from here we can find IF, or if IF is given we can find RF. And IF from the graph we can find EAO. So if we know IF we can find EAO, or it is simply sometimes called EA. So this current is now given, the load current IL. From here we can find EA. IL is 180. VT is given, RA is given, so we find EA. So EA is 265 volt. Now we come to the table, 265 is between these two. So IF will be between these two, so it is about 15 ampere. But the professor in his solution has taken 14.78. I don't know how accurately you can go to this point, but he has also mentioned that any approximation will be acceptable. So if we take 15 ampere, it will be okay. But just to be trying to find more accurately, I'm now using the graph. And so from here you can see this is 260, 280, so mid is 270, half of that is 265. And so if we draw it, then it is almost like 14.75 or 78, whatever. So we can use this. But for you to follow the match, I'm just using whatever the professor has calculated. Okay, so IF is known. Now from here we can find RF. So 330 is fixed. IF is 14.78. So RF is 22.3. So this is the total field resistance. And from here now we need to find FCR. So this was the formula. RF dash is fixed. RF we have calculated 22.3. So FCR will be RF minus 20. So 22.3 minus 22.3 ohm. So the variable resistor has to be adjusted to 2.3 volt to get this output current. And now question 4 or 1.4, find the maximum possible load current at a terminal voltage of 220 volts. So maximum possible load current. So to get maximum possible load current, we have to have the maximum field current. And the maximum field current will only be possible when FCR is 0. Maximum possible load current will occur when IF is maximum. And IF will be maximum when FCR is 0. And so in this formula, FCR is 0, that means RF is equal to 20 ohm. We will use this to calculate IF. And putting in the formula, the IF will be 16.5 ampere. Okay, with this, we have to calculate EA. Go into the OCC table. 16.5 will be again between this and this. So you have to guess it is about 268 and 272, and the gap is of 2. We need 16.5, so I guess it will be about 269. So from the table or the graph, let me see the graph as well, and 16.5 is somewhere here, and if we go here, then it is between 260 and 280, so 270 or 269 volt. And putting in this table now, IL maximum will be 269 minus VT over RA, so it is 190 ampere. So this is the maximum as against 112 for the FCR 10. So when FCR is 0, you can see the load current has increased tremendously. And finally, question number 5, find the terminal voltage when the it changed to, okay, sorry, the spelling is wrong, speed. And the speed is changed to 110 RPM. Now, earlier all calculations were done with the speed 850 RPM. Now, what will happen if we change the speed to 110 RPM? We have to find the terminal voltage. FCR is 10 and the load current is fixed to 200 ampere. So these are the values that are given. We have to find VT. Okay, same formula. Now this is new EA for 1100 RPM. Remember, the OCC graph will be different for every RPM. So at this RPM, we have to find this value. Find EA new, we need to find IF new. So for this, the current will be obviously a new value because we are on a different table. And formula for IF new will be same IF new will be VF divided by RF new. And RF new is the same like a 10 will be FCR, 20 is given, so it is 30 ohm. So RF IF will be 11 ampere as we got in the first part, so same value. Now EAO was 248 in the question number 1.1 for 850 RPM. But we have to find new EAO for 1100 RPM. For that we have to use this formula. Now these are two, this is the reference EAO, this is the new EAO, and this is the reference speed, and this is the new speed. We can rewrite it like EA new and EA for 850, NM new and this was the original one, and so EA new from here will be this formula, plugging in the values here. New speed 1100, old speed was 850, EAO old was 240, therefore EA new is 320.9 volt. And so plugging in this formula now, 320.9 current is given fixed, 200 RA is fixed. So VT new will be 270.9 volt. So I hope you have been able to follow this lengthy question. Let me know through your comments. Thank you.